Okay.
Let me tell you some things about maybe classical enumerative geometry. So the last two words in this title before I tell you about some new ideas about using equivariant homotopy theory to say to basically refine classical statements in the presence of symmetry. So enumerative geometry dates back to the ancient Greeks, and it asks questions of the form: how many blank? And I'll say something maybe a little bit silly here. It expects integral answers. Which, okay, if I'm going to count something and I'm going to ask for an answer, it makes sense that I would get an integer. But I really want to sort of differentiate between what I might call classical enumerative geometry, which is asking geometric questions and just seeing an integer, right? We're just counting objects sort of on the nose, versus something we might call abstract or refined enumerative geometry, where we ask questions and we count things that are maybe strictly richer objects than integers. So things like symmetric bilinear forms, or we'll see finite G sets that are encoding strictly more than a set, just a little bit more data maybe. So one of the earliest examples of this dates back to Apollonius in around 200 BC. And the question is the following: how many circles are tangent to 3 drawn on the plane? And this is where we see the first advantage of having an iPad talk, which is you don't have to watch me try to draw a circle on the board. So, okay, I can take 3 circles that look like this. And this is the hard part of doing it on the iPad. I'm gonna try to draw another circle that is just tangent to all 3 of them. I may have to move it around just a little bit, but I get something that maybe looks like this. We've got another circle out here. And I could keep drawing these and sort of ask how many we have. And so there's a few more of these, but the answer, at least to this question, is that there's going to be 8 circles. And this is the, if I have it right here, Joe Harris and David Eisenbud's book 3264. This is the cover of this is the art of 8 circles tangent to 3 drawn on the plane. Another classic example dates back to Bezout in 1779. And this is the following question: how many points of intersection between planar curves of degrees m and n? And Isaac Newton had most of this actually worked out about 100 years earlier. There were some sort of subtleties about working affine space versus projective space that weren't fully worked out until maybe a little bit after Bezout's time, actually. But this is the question of maybe I draw a degree 2 thing, something like a conic, and I draw a cubic, and I look and I count how many points we have for multiplicity. And it was sort of understood even to Newton in the late 1600s that this should be proportional in some sense to the product of the degrees of the polynomials. And again, this is Bezout's theorem. The answer to this is you see m times n points when I count appropriately. And there's some fine print for these problems, right? We should be, in general, over the complex numbers. We shouldn't be picking our things so that I see infinitely many solutions or 0 solutions. We should just sort of be picking things at random and studying what we see. And let me give one more example, which dates back to Salmon and Cayley in, I think, 1849. And this is this famous question of how many lines lie on a smooth cubic surface. Okay, and so what is a cubic surface? And we'll talk a little bit more about this example, but we'll go into this in detail in a bit. But a cubic surface is the vanishing locus of a degree 3 homogeneous polynomial in CP3. So this thing right here, this should be degree 3. And we also want the polynomial to be smooth here. Okay, so what are we asking when I ask how many lines lie on this thing? I'm in projective 3 space. So this is an example. This is what a cubic surface looks like if people can see the video. So what we're asking is, on this surface, can I walk along it in such a way that I'm tracing out a straight line through projective 3 space? That's the geometric question. The algebraic question is how many equations for lines in projective 3 space are valid when you plug them into the equation for this cubic surface. And the answer to this is that you see 27 lines. This is sort of one of the great famous theorems in this era of algebraic geometry. Okay, so what is interesting about all of these questions? What's sort of making them all? What sort of makes it tick? So there's two things happening here, which is the first one is that the answers aren't boring. And boring is a technical term in this talk that might mean 0 or infinity. I'm not asking questions that, I don't see any solutions or I see infinitely many solutions. I'm sort of asking something that lies strictly in between these. I get a finite amount of data that I can latch onto, and I can study that and ask a lot of questions about it that are really fascinating. But the second thing, and this is implicit in all the questions that I've been asking, is there's some independence of initial parameters. So what do I mean by this? I mean, I asked this question of how many circles are tangent to 3 on the plane, but I didn't tell you which 3, right? So baked into that question being well-defined is this idea that it doesn't actually matter which circles you picked. If I wanted to do a computation, I could pick circles, right, and compute the sort of tangency locus in a moduli space of circles and get equations for the 8 that are tangent to them, but somehow that number 8 shouldn't depend on the parameters that I started out with. And one of the first people to really kind of flesh out this idea was Poncelet in the early 1800s, around 1814. And Poncelet was trained in the French School of Mathematics at the time. He had gone to college and studied algebra and geometry, and then he was conscripted into the Napoleonic Wars. And he was taken as a prisoner of war in Russia. And during his time in prison, he was trying to sort of recall all the math that he had learned. And he found that the algebra didn't quite come back to him, but the geometry did. And he was very famously sort of taught other prisoners at the time. And he was thinking a lot about projective geometry in the style of the ancient Greeks. And he came up with this idea that was, maybe more of a philosophy than a precise idea. But he called this the principle of continuity of number. And what this means is that if I take my 3 circles that I started out with, so maybe let's grab this picture here. The idea is that if I took one of my starting circles and I deformed it slightly, if I kept it a circle, right, but maybe I shifted it over, or I grew it, or I shrank it, the other 8 solution circles will adjust in order to accommodate tangency. But in particular, that's all they'll do, right? They won't just disappear as solutions as long as I'm not moving into some sort of degenerate place. So it's this idea that the answer is invariant under small parameterized changes. And we have a more precise word for what this means now. We might say this is something like a homotopy invariant. And I'll put this in quotes because I don't maybe mean this quite as precisely. Okay, so at the time in France, you sort of either had to be doing something that helped civilians or that helped the war effort, or you had to be Cauchy, and those were your 3 options as mathematicians. He was sort of the only one who was allowed to do very abstract mathematics. And Cauchy was very into equations and into very precise mathematics, and he despised Poncelet. They really hated each other and famously got into a screaming match on the streets one time. And consequently, Poncelet didn't end up continuing in mathematics. He ended up working on water turbines for the rest of his life. But Schall and Gergon and a lot of these people, and later German mathematicians like Jakob Steiner and Schubert, ended up picking up these ideas and really sort of championing what Gergon had done. And Schubert, in the late 1880s, sort of took this idea and maybe recast it. And he said, we're going to call this the principle of conservation of number. This is sort of essentially the same idea, but this is now what sticks when we talk about the history of enumerative geometry. So Schubert's stuff it was very, I just found out recently, it was very recently translated into English. And his math is just insane. I don't know if you can see my screen, but it's just like equation after equation of him answering these questions and getting the right answers all of the time, but it being sort of completely unjustified. And so at the turn of the century, Hilbert listed among his problems, Hilbert's 15th, and it was the following. It was put Schubert calculus, or what Schubert called the calculus of conditions, on a rigorous framework. So what was Schubert doing? I mean, he was answering all of these sorts of questions about how many lines do such and such, how many planes do such and such, how many curves are, passing through points and tangent to lines, these sort of beautiful questions. And he developed a calculus for doing these things, but didn't justify where it was living. And I want to give some sort of maybe ahistorical justification about what was happening here. And it was the following idea that you might call the Poincare-Hopf theorem. Okay, so it's a statement about in vector bundle theory. And what it says is let E to M be, let's say, an oriented rank n vector bundle on a smooth, oriented, compact n manifold. And let's let sigma from M to E be any general section. I'll put general in parentheses because we don't actually need it for the statement of the theorem. Then the following is true. I have that the Euler class of my bundle is equal to, if I sum over the points in the zero locus of sigma, and if I'm general, I will actually just have sort of a zero-dimensional zero locus. And if I sum something that might be called the index of sigma at P, then this is one way to compute the Euler class. Okay, so what's happening here? I've got some sort of global solution, and it can be computed as a sum of local contributions. So let me make this maybe a little bit more precise with an example. So an example is the following statement, which we actually have already seen. So if I take these two line bundles, O of M and O of N, over CP2, I can ask what the Euler class of this thing is, or what its second Chern class is if I'm over, I'm over the complex numbers right here. And we can compute this basically just from, easy properties about Chern classes, that this is M times N. And now let's look at this Poincare-Hopf theorem and let's see what this is telling us about the situation. If I take a section of here, it's a section of each bundle. So maybe let me call this sigma F and G, where I've got each of these sections. And what is F? F is, it's a homogeneous form of degree M in the coefficients on CP2. So it's a planar curve of degree M, and G is a planar curve of degree N. So those are the sections of my line bundles. And what am I saying? I'm saying that this Euler class that I computed, this M times N, one way to interpret it is if I look in the points of this, where this section vanishes, or phrased differently, where each of the individual sections are vanishing. And if I count these with some local index, then I get M times N. So let me draw a slightly different picture here for a cubic and a conic. So I go to each of these points that are in the common zero locus of my sections, and I sum up what it's contributing to the problem. And I have to make this idea of a local index precise. But one way, if you're at an isolated zero, one way to look at this is to take the intrinsic derivative of your section and compute a Brauer degree of that on charts. So if I go to each of these points, let's say maybe I have a +1 here, +1 here, because these are all transverse intersections. It's not really doing anything on the chart. And then here I've got a +2. One way to see this is if I deformed this slightly below the line, I would see 2 transverse intersections. And when I add all this up, this is equal to 6. So I'll just write kind of a really silly thing, which is 6 is equal to 2 plus 1 plus 1 plus 1 plus 1. And this is supposed to remind us, right? These two formulas are supposed to be the same here. Okay. Let me do another example. Let's work over the Grassmannian of affine 2 planes in 4 space. And what this is telling me, I've got 2 planes passing through 4 space, and when I chop out the origin and mod out by scaling, I'm getting a line in projective 3 space. So these questions about how many lines on such and such, this is sort of the right moduli space to look over. And then I want to encode, like, let's say I want to solve the cubic surfaces problem. I want to encode the condition of a line lying on a cubic surface as something lying in the 0 locus of a section of a particular bundle. We should be maybe a little bit careful about this, but I've got a tautological bundle, and I can dualize this. And one way to get a section of this thing is to take a linear form on your whole ambient vector space, on the whole c to the 4th. And I could take maybe a third linear power of this. And what this would give me is a degree 3 form on C4. At least that's one way to produce a topological section of this. And I could take the Euler class of this, and it's a really lovely computation in Schubert calculus, in the cohomology ring of the Grassmannian, that this is equal to 27. And again, just to be super clear, what's happening here? A section here is some sigma f, where f looks like this. F is a cubic surface. And what this section is doing is it sends a line to 0 if and only if the line lies on the vanishing locus of f. Okay. So this is one way to attack enumerative geometry problems, is to set these things up as vector bundles and then apply this Poincare-Hopf theorem. And I should double back to say what this tells us about conservation of number. One perspective you could take on conservation of number is the idea that the solution is an invariant on the bundle. And doesn't depend on the choice of section. So this is this idea of I have 27 lines on any smooth cubic surface. Reason for this is that if I picked a different cubic surface, right, that would just give me a different topological section here, or a different algebraic section. But in particular, I mean, the Euler class isn't going to change because it doesn't depend on the section. And Poincare-Hopf just tells us that is one way to compute it. Okay. Any questions before we keep going? Probably a good pace to pause. All right. If not, maybe let me say a little bit about what happens over R. So there was this word oriented that I kept throwing out in Poincare-Hopf. I wanted an oriented bundle over an oriented base. And what this allows you to do is when I do this computation, maybe I've got my bundle over M here. When I have a point downstairs and I'm looking at the fiber up above it, it allows me to pick charts in a compatible way. If I know both things are oriented, let's say I'm over C, when I look at the intrinsic derivative and I want to compute what it's contributing to my problem, there's no ambiguity about orientation. So there's no issue of maybe like flipping a sign on top and bottom. And again, if I'm over the reals and my base manifold is oriented and the bundle that I'm looking at to solve the problem is oriented, again, I can run this game because I have a nice choice of charts. But in general, a lot of the problems that you want to solve, the manifolds themselves won't be oriented over R, and the bundles won't be oriented. So you want to get away with something slightly weaker. So one thing I might be allowed to do is to maybe I could assume, sorry, I shouldn't say assume, let's say, I can ask the bundle and manifold to maybe not each be oriented, but have some compatible notion of orientation between the two of them. And this is something we call relatively oriented. Okay, so what do I mean by relatively oriented? An orientation, right, is it's a trivialization of the determinant bundle. And what this is telling you, right, is it's telling you that when I look at my transition functions, they all have positive determinants. So I'm not worrying about orientations. And if I want to look at sections of these sorts of things and I want to do these computations, I might ask for something like this. I might ask for this thing to be trivial. Or this is maybe a little subtle, but being trivial in this case is the same as being the square of a line bundle. But this ends up being maybe a slightly better notion as you go to work over other fields. So this is the idea of having a relative orientation. And this tells me when I look at sections and I want to look at their intrinsic derivatives, I have a well-defined way to associate an index to these things. Okay, so let me decorate this isomorphism with a row. And there's a theorem that should be attributed to a lot of people, but let me just give you a place to look for it. This is in a paper of O'Connick and Telemans from 2014, and says the following. There exists a well-defined, what they call absolute Euler class. Associated to a relatively oriented bundle. And I need some assumptions here, right? I want the rank of the bundle to be the same as the dimension downstairs. I want to be working over something that's smooth and compact in the base. And maybe let me just like say a ... here. And what we might write this is like n, maybe let me write E of my bundle, comma, row. Let me continue the statement of the theorem. And given two choices, of relative orientation, say row and row prime, you could ask how they differ. And the answer is it can only ever affect your answer up to a sign. Okay, so this is one of the reasons it's called an absolute Euler class. Is the absolute value of the answer you're getting is independent. And morally, why is that the case? It's because if I changed my relative orientation just slightly, what it has the effect of doing is basically going through, and in each of my local contributions, it's flipping everything. Like it's turning one of the orientations over. I get multiplied by a -1 everywhere, and that affects it, but only up to absolute value. Okay, so there's a beautiful example of this, and this is a very ahistorical talk, so I'm telling you a theorem from 2014, and I'm going to give you a corollary of it from 1942. And this is work of Segre. This is also Fanashin and Kharlamov. Cass and Wickelgren deserve some credit for this as well, Benedetti and Silhol, and some other people I'm probably forgetting. But let me attribute this to Segre because this is where the idea first appeared. And it's basically the following computation. It's the computation that the absolute Euler class of Sim3S dual over GR24 over the reals is equal to 3. Again, with some choice of, maybe let me throw an absolute value here. Okay, so what is this telling me? This says the number of lines on a real cubic surface is 3. And this is slightly wrong, right? It's not the number, it's sort of the sum over the local contributions. So let me say what this local contribution is. If I have a line on a real cubic surface, so let's say L on X is a line on a real cubic surface, then what am I able to do? I can say something slightly different about this that I wasn't able to say over the complex numbers, and it's due to the presence of maybe a more subtle discussion about orientation. If I've got some line, then I can look at the tangent plane of that line and I can sort of travel along the cubic surface and let my tangent plane vary. And as I go out to infinity, my tangent plane comes back, and it either comes back with the same orientation that it started out with, or it comes back flipped. And what you're asking is this loop, because this is a copy of S1, is this lifting to the double cover of SO3? So lines on X, to each of them, I can associate a class in pi1 of the frame bundle. And I call my lines hyperbolic or elliptic, depending on what the class is. And so what this theorem is telling me, so this theorem right here, another way to phrase this is that if I sum over the lines on X, and I didn't sum a 1 every time I see a line, right? That's how I would count the lines. And instead I summed something slightly different, we might call the topological type of the line, which is this data right here. I'm always getting 3. Okay. And I probably should have thrown this theorem before I started talking about this, but there's a theorem of Schläfli in 1858. Maybe this is why we shouldn't expect to see all 27 lines. It says on a real smooth cubic surface, you're going to see 3, 7, 15, or 27 lines. So I guess sort of going back in history, this was the first result. This tells you effectively that conservation number breaks if you're not over the complex numbers. You won't always see the same solution. But what this discussion about relative orientations is telling you is that if I don't count the lines themselves, if I count something about the lines, I can get a well-defined answer. And this leads us down sort of a long rabbit hole of very beautiful enumerative geometry that would be a slightly different talk. But so let me stop here and transition into a discussion about equivariance. Before I do that, are there any questions?
Yes, I'm wondering what's the idea of the square in the definition of relative orientation, the square of the line bundle. Is it like positivity?
Yes, exactly that. So yeah, if you're square, then all of your transition functions will be squares, so their determinants will be positive. This is really, I mean, this, in the way that I phrased it, this is actually due to Morel in 2012, and this is a slightly different definition. So it predates the Koenig-Tellman by a very short amount of time. But this makes sense over arbitrary fields. It's weaker than asking this to be trivial, right? Asking it to be a square of a line bundle. And when we start doing things in like quadratically enriched enumerative geometry, this is the notion that we want. But over the reals, yeah, we should really probably just think about this as being trivialized. Okay. Okay, so let's talk about equivariance. And I want to be back over the complex numbers now. So back in the classical setting. So I'm going to say a cubic surface V of f is symmetric if f is a symmetric polynomial. And there's another way to talk about this, which is, so this is a reasonable definition, but I could also think about S4 acting on CP3, where this action is by permuting coordinates. And maybe let me make this into a sentence here. So a cubic surface will be symmetric if and only if under this action, this thing is an S4 space. In other words, it's being mapped back to itself. And I start acting on CP3 in this way. One thing that I notice is that this action is linear in the sense that it doesn't bend lines in projective 3 space. So if I have a line on a symmetric cubic surface and I act on it via S4, I get another line, and that line will still lie on the cubic surface. So it's a very nice question to ask. What are the S4 orbits of the 27 lines on a smooth cubic surface. And again, this is the same sort of type of question as the classical ones, but now there's a little bit more symmetry happening. But there's, again, this is baked into the question, right? Is it, does it depend on the choice of smooth cubic surface? Right, I know by the classical account I'll always have 27 lines, but it's not clear, right, that S4 will act on these 27 lines in the same way. In other words, it's not clear that I'll get an answer that is something like a G set rather than just a set. And a more general question we can ask is there an equivariant version? Is there an equivariant conservation of number? Okay, so this is where I'll get maybe just slightly technical. So apologies to the people who aren't homotopy theorists in the audience. But so here's the setup that we care about. So I want to do a very classical thing but just with a little more equivariance here. So let's let E to M be a rank n. Now I'm going to assume we're complex vector bundle over smooth compact G manifold M. And what I really want to say is this is like a G vector bundle. So I want an action of my group on the fibers, I want an action on the base, and I want the projection map to be compatible. And this base manifold should have the right dimension to get some sort of Poincare-Hopf statement. So this should be of complex dimension n. And let's let sigma from M back up to E be any G equivariant section with simple isolated zeros. And I haven't said anything about G. Maybe for the purposes of this talk, let's assume it's finite. Okay, so an example of this, right, is the setup above, right? I have GR24 over C. I have S4 acting on this by permuting the C4. And this induces an action on the tautological bundle, and that gives you an action on the entire bundle, Sim3S dual. So I've got an action here. And I could take all kinds of sections of this, but the sections that I care about are the ones that are equivariant. So I want S4 equivariant sections, and this will be, basically the sigma F will be equivariant. An equivariant section if and only if V of F is symmetric. Okay, so this is the setup that I care about. And the simple isolated zeros is a technical assumption. And so here's the following theorem. So I'll state a version of the theorem, and then we'll work towards getting a usable version of the theorem. So the version is in the setup above. If A is any complex-oriented G ring spectrum, then we get a well-defined Euler class. And this is, I'll write this as N of E, and I'll write a subscript G. And this is going to live in the pi naught of A. And it has the following property. It can be decomposed over its support in the same way that the Euler classes up above in the Poincare-Hopf theorem can be decomposed over the support. So what do I mean? So I assumed that I have simple isolated zeros. So I'm going to look at all the different points in the zero locus of my sigma. And I want to look at each point together, but I want this G action happening, right? So I want to look at not one point alone, I want to look at sort of its entire transitive orbit. So I'm going to sum over the G times P. Let me write this as like maybe a subscript or a subset of Z of sigma. So I have a point and it has some orbit, it has some stabilizer, and I want to transfer up from its isotropy the quantity 1. Okay, so for the uninitiated in equivariant homotopy theory terminology, this 1 exists basically because each of the equivariant homotopy groups of A is a ring in pi naught. And this transfer exists basically because I can, in the same way maybe like induction of representations exists. This is something that's baked into the data of having a G-ring spectrum. Okay, so I'm able to look at these quantities and I want to transfer this data up. So this leads you to a question, what homotopy, what cohomology theory should we use? So let's maybe double back to Poincare-Hopf and say, okay, well, what was actually happening in the Poincare-Hopf statement? I had an Euler class that was living in integral cohomology, and I was decomposing it over its support. I was integrating sort of each of the individual pieces of this, and then I was summing it up, and I was getting something in pi naught of hz, which is z, right? And so I'm wanting some cohomology theory whose pi naught is baking in this data that we're caring about. And I would really I would want pi naught to be equal to the Burnside ring of my group G. And what is the Burnside ring? This is basically isomorphism classes of finite G sets where you group complete with respect to addition and you get a multiplication coming from Cartesian product. Okay. So here's our first naive attempt. So the naive attempt is just to say, okay, well, I was using an Eilenberg-MacLane spectrum. I was using HZ to do classical enumerative geometry. And I might want to use something like that. I might want to use the Eilenberg-MacLane spectrum attached to the Burnside-Mackey functor. And there's a problem with this. And this is a problem that's kind of unique to equivariant homotopy theory, which is that Eilenberg-MacLane spectra are not in general complex oriented. Okay, so they don't really receive a theory of Euler classes. The reason being that they're integrally connective as spectra, and I can sort of tell you by a picture what's happening here. I could look at 2 points including into a 1 sphere. This is S naught. And this I'm going to call S sigma because I'm going to let C2 act on this thing by flipping. And when I include this lower dimensional sphere into a higher dimensional sphere like this, and I'm start to flip S naught, if there was no action, right, I'm allowed to just take this point up at the North Pole and homotope it down. And hey, I see this map is null homotopic. But when there's this action, you can't move the North Pole down in any sort of reasonable way. And so I get these classes that are basically Euler classes of spheres that I need to be able to give Tom classes for. And if I'm integrally connective, I won't have Tom classes. These will vanish. So this is a really interesting feature of equivariant homotopy theory. Okay, so that attempt fails. And attempt number 2 is, yeah, was there a question? Oh, okay. Attempt number 2 is maybe let's slightly give up on this assumption that pi naught would be the Burnside ring. And let's just use basically the first ring spectrum that was shown to be complex oriented, which was by Siegel, which is complex equivariant K theory. Okay, so what does the theorem from before tell us? The theorem says I'm going to get something living in pi naught of complex equivariant K theory. And let me tell you what that thing is. If I take pi naught G of KUG, I'm looking at the equivariant topological K theory of a point. In other words, I'm looking at the G representation ring. And so the theorem is telling me, hey, I'm getting a well-defined answer in the G representation ring. And what the theorem implies is that the G representation, the permutation representation, attached to any equivariant enumerative problem. And by any, let me put an asterisk, any that can be encoded in this setup that I defined above, having these sort of equivariant section. the permutation representation attached to that is conserved. And what that means is that I can, anytime I have this sort of problem, I could go in, I could solve for my solutions, I could let G act on my solutions. And what I would see then is that the